Hi everyone, welcome to the week 11 of this tutorial session. Today we are going to talk about the emission of electromagnetic waves or radiation by an accelerating point charge. So last week we have seen what does give rise to electromagnetic radiation. So there we saw that if we oscillate a charged plate, so in this way, so perpendicular to this oscillation at each point, there is going to be this electric field component and magnetic field components that will be generated. Now, in this week, we are asking the question if you have a point charge, so let's say Q, so if it is moving in this direction, so how it is going to emit radiation? What are the conditions under which it is going to radiate electromagnetic wave? So we will explore that. Before going to that, I will wait for 2 or 3 minutes so others can join. Okay. So I think uh, we can start now. So for the again, we have to go through the not this time, but it's okay to recall some of the equations. So first one, if so, we will recall that Maxwell's equation. So the first is del dot E is equal to 1 over epsilon naught rho, that is due to the Gauss law. And then second one is del dot V is equal to 0. So it means that it's a solenoidal kind of field where whatever is being whatever is going through a point is also coming back to that point, whatever field is going through that point. So that means it's a closed field. So that's why divergence of this closed field kind of thing has zero. Then you have the third one where the curl of electric field which gives a magnetic field. So and that is changing with the time. So it's essentially Faraday's law where you have seen that if you move some coil of wire in static magnetic field, you can induce a voltage across the both end of this coil. Or you can what you can do, you can put the coil as it is in a steady state, like at a place. You don't have to move that coil, But somehow, if you are able to change the magnetic field with respect to time, then you will see that there is the voltage generated across this coil. Other scenario can be where you keep the coil at its edge and just change the magnet, like you move the magnet. So it's a relative phenomena where the in the what do I mean by relative is that the velocity between with respect to the magnet and with respect to the magnet uh, will define how the voltage are generated. It does not matter whether you move the coil or you move the magnet. Both are the same effect. Just like if you are in the magnet frame of reference, so you will, if the coil is moving, so you will see that okay, its coil is moving, and that's why the voltage is generated across the coil. But if you are in the coil frame of reference, and it is the magnet that is moving, so that's why voltage generated. So it's a relativistic phenomenon, means that you, there is the net relative change in the velocity is uh, is responsible for the voltage generated across the coil. And then the fourth equation is del cross V is equal to mu 0 J plus mu 0 epsilon 0 del E over del T. So what does this mean is that okay, so this is, you have seen that this is due to this Ampere's law, but uh, there is this additional terms mu 0 epsilon 0 del E over del T that you have seen that it, so in Ampere's law, the current flows without stopping anywhere. Like if this current is I here, so current is also I here. But let's say you have a capacitor in between. Like this is the wire, then they have capacitor, then again the wire. So if the current is flowing, those charges are being accumulated here. So here the current is J, current density is J, but here it's changed, right? Here it is zero because there is no charges inside the capacitor. But the charges that are being accumulated, they will give rise to a changing magnetic field, a changing electric field, and that changing electric field is also responsible for the generated magnetic field. So this is the modified equation that was present before the Maxwell. So Maxwell added this term, and now you have the whole Maxwell equation. Okay, so this is the bit of background, and in the source free region where rho is zero and the J vector, I mean the charge current density is zero and the charge density 0. So del dot E is 0, del dot B is 0, del cross E minus del V over del T, and del cross B is equal to mu 0 epsilon 0 del E over del T. So in last few sessions, we have been dealing large extensively with these equations where we were deriving the electromagnetic wave equation, then finding its solutions, like which kind of solutions are the feasible solution for this electromagnetic radiation. So we found out that for it should be a like exponential function, but it should depend on this fx f f. It should be a function of x minus vt. So x and t are linearly related. There is no such dependence as x square minus t square or something. So x square minus c square t square. There is none of this kind of dependence. So it linearly depends on x, and the difference. It's so whatever the function is there, like exponential can be, but the exponential though in, but the value that we are putting inside the exponential should be x minus ct or x plus ct, not x square plus c square t square. So it's not quadratic or anything. It's a linear in nature, and so that we have found out. And now about the radiation field. So why why a move? Okay, so if we have if we have a point charge q, so if it is moving with a constant velocity, that means it is not accelerating. It has some initial velocity v. It was moving with, it keeps moving with that this velocity. Then what happens if you draw a Gaussian surface across like this? So if, let's say, it at this time it is here. So if you draw the Gaussian surface like this, so if you, and then on that Gaussian surface, if you draw the electric and magnetic lines, so you will see that the field lines are just readily outwards. And if it is moving with constant velocity, then you will also find that at this point somewhere here, it will have the same distribution of electric field and magnetic field. So where it will be like such that electric field lines are also like, if q moves here, so it's the same system just translated with velocity, translated at a distance of, let's say, if the velocity is v and the time taken is t, so the distance that it travels is vt. So it's the same system, no changes happen in the distribution of electric and magnetic field. That's why the charges that are moving with a constant velocity does not emit any radiation field. So the question is, what does give rise to the emission of radiation? Okay, in case of point charges. So it's like this when the point charges are accelerating. So if it is moves in accelerated manner, what happens? The field lines, should be uh, in any Gaussian surface. If you draw any Gaussian surface that is at distance of c into t, means c is the uh, velocity of radiation in this vacuum. So outside of that, the electric field lines will have still the same distribution, but because this charge is moving with velocity c inside that Gaussian surface, you will see there that there are some tangential components of electric field are appearing, and those tangential components are changing with the time also. So what happens is that because it's accelerating, so that amplitude of that tangential components are also changing. So what happens that this change in the electric field, now you see that there is this change del E over del T. So, so you can automatically guess that if the electric field is changing, so there will be a generation of a magnetic field. So this is how this magnetic field and electric field are generated from a point charge. So the first question is, okay, before I, before I go to this, I want to share something with you. So, okay, so I will share something here on my screen. So, uh, if you can see, here is the, if you go at this site, you can just play around with this. So here you see, uh, il and charge is moving at this constant speed. Okay, so you cannot see any changes in the distribution of this electric field lines. But what happens when you increase the velocity? Okay, so you see, if we changed a bit of this accelerating, so if change the velocity a bit, so you can see there is this tangential component that are appearing now. But if it is so by changing the velocity, what we have done is that we have just giving it some acceleration, because the delta v is not zero with the time. So here you can see if I'm playing around with this, so it is radiating and electromagnetic. It's the electric field lines are changing, but if you like don't accelerate it, so the field lines that are there are very uniform. So it means that with if it is moving with a constant velocity, it won't radiate. But if you just disturb it a little bit, let's say a little bit of disturbance you give, so, so if it is here and if we run it, so it's just moving and no acceleration. But if just perturb a little bit, you can see that field lines start to emit. So that delta V is not zero. At the moment when we change it, it's a delta V is not zero. Okay. What happens at constant speed? Is there a still disturbance? No, we don't see it. But if you suddenly change it to charge like velocity, we can see that field lines are emitting. Now, if we if, okay, so here you see, so it's like this field, this charge is going up, then it's coming back, so it's kind of performing an SHM. So uh, the field lines are changing in such a way. So they are not radially outward anymore. They have some tangential component. Okay. And this is the charge that is, I think it's moving in a circle. So you can see that it, so if anything that moves in a circle, it has a acceleration. So that's why it it is radiating. So okay, and then so that's it. You can explore this website for your understanding how this, and you can read it here. But you can see in the animation like how this accelerating charges are radiating. Okay, so it is moving in x direction. So you can see that the field lines in it's moving in y. The field lines are changing in x. Okay. Also, there is this Mathematica inbuilt, like they have built a script for seeing this. So if you just play around with this one here, so you can actually see how this, if the velocity is like this, okay, it's frozen. We can, I think we can play around with this also. So here, sun is legend. So if I change the time, so you can see with the time, let's slow down a little bit. Let's say half of the light velocity, the charge particle will be. So you can see if we go further in time, so at some point, this velocity into time means this point 0.5, this, so you can see at this, like the charge is moving in x direction, but this, this field is not radial anymore. It has some tangential component here, here, and here. And also, one thing you can notice that the field lines are more in this x direction other than in negative x direction. So that's why, because the charge is moving now like in this x direction, so we can expect that it will have more field lines in positive x direction and less field lines in negative x direction. And also you can see that there are tangential components that are present here. So this component changes with the time and it gives rise to the magnetic field and electric field. Okay, so you can explore this also. Okay, that's it. So let us go to our first question. The propagation direction of an electromagnetic radiation is. So here we are given that propagation direction of electromagnetic radiation is E cross B, B cross E, B vector, E vector. So you know that the propagation direction that is essentially given by the Poynting vector. So it does not matter in which medium you are. Like if you know how to calculate the Poynting vector, you will know what is the direction of the propagation of any electromagnetic radiation. So Poynting vector is given by the cross product of E cross B, not the other way around, means not B cross E. So the first one is the correct answer. And in case of electromagnetic radiation, what happens that if anything that is, let's say this is propagating in x direction. So okay, so this is x. If this is if if this is y, so this is z, right? So the electric and magnetic field. So like this electric field will be like this, and the uh, this and the magnetic field like will be like this. So electric field is like this, and the magnetic field is like this. So we can it's like they are perpendicular to the propagation direction. So if you take the cross product of that, you will find out the direction of propagation means in which direction the radiation is traveling. So it's simply given by E cross B. And I think in last class I have also told while discussing about this electromagnetic radiation emission from the charge plate. And the second question is the electric and the magnetic field components directions emitted due to accelerated point charges are. So the question is like if you have a point charge, like in the case here, so this this black line represents the direction of r cap, means the some distance from the point charge at given instant of time. So it is being asked from us like what if this is the direction of propagation of this radiation, then what is the electric field and magnetic field components at that point. So if any point R has this kind of direction, like that is going alongside the black arrow, so we can see here that the electric field and the magnetic field, even though the electric field is lying in plane, that you can see that this arrow, but it's perpendicular to the direction of propagation. And also the magnetic field. So magnetic field is like this field is like this cross product is like this. So you can see that magnetic field is coming out of the plane. E cross B will be like this, and that is giving you the propagation direction. So, but again, so this magnetic field is like this. So this is the propagation. So you can see this is this kind of okay. So you have this. This is the uh, propagation direction. This is the electric field, and this is the magnetic field. So they are perpendicular to like this. So if you do the cross product, you will find out the propagation direction. So and still you can notice that this electric field, this electric field is perpendicular to the propagation direction. This magnetic field also perpendicular to the propagation direction. So this and this are perpendicular. This and this are perpendicular. So both E and B are perpendicular to propagation direction. So the electric field E is perpendicular to R and B is perpendicular to R. So E parallel to R and B parallel to R both are wrong. So but if B perpendicular to R and E perpendicular R to R is correct. So option E is correct. alongside A and B. But okay, so our next question is the direction of pointing vector, which has of the following relation with electric and magnetic field component emitted from accelerated point charge. So I just told that this this pointing vector is nothing but the direction in which this electromagnetic radiation is traveling. So that depends on the cross product of E and B that we know. Okay. So if you know in which direction, if you know the direction of your electric and magnetic field, then you can easily calculate the direction of pointing vector, and that is given by simply as E cross. So uh, okay, so we can calculate the pointing vector. So that is E cross V. Now we are being asked like the amplitude of pointing vector depends on the r in the following manner. So if we have a point charge that is accelerating, so how this electromagnetic, how this pointing vector amplitude uh, depends on the depends on, like, if you go r distance away from the point charge, so in which manner the pointing vector amplitude will decrease. So actually for this we need to understand how the electric field and how the magnetic field components are dependent on r, and with that understanding we can see how this pointing vector is decreasing or increasing with the distance. So for time being, this S vector is proportional to the 1 over r square, because here you can see S is proportional to E and also B. So if we can guess that if E is proportional to 1 over r and B is proportional to 1 over r, then the emitted amplitude of, so then the amplitude of this emitted radiation, like the pointing vector amplitude of this emitted radiation, will be proportional to 1 over r square. Okay, we will see in a bit like how this electric field components depends on this. That is our question number 5. So we can just calculate it. So I will share my screen with you. So the thing that we are being asked is how this electric field actually depends on this thing. So first we can understand this in this way, that so you have an point charge. So if it is this acceleration is zero. So if you make a Gaussian surface, let's say a circle, so you have this point charge Q, and I make Gaussian surface. So you draw the field lines. Draw the field lines. Okay. So for understanding, these are the like it will also extend outwards in the same fashion. Okay, let me draw it more clearly. So what we can we just put this in the center of the charge, and then we can take the field lines like this. So like they are uniform. But what what I'm trying to say here, at this boundary, if you notice, so if they are this is the positive charge, so they are radially outward, the electric field. And what happens? So this is the case for where B is equal to 0 or or B is equal to some constant. Why constant? So just we have seen the simulations like illustrations where you can see that field lines were not changing uh, even though this charge, this one was moving. This was moving with some velocity. Because what happens in the frame of reference, in the rest frame of this charge, it is not accelerating with respect to anything. So it will not emit because in this case the field lines will be the same for this accelerating charge in its frame of reference. And also in our frame of reference, if we see, so what will happen that the field line will change, uh, will not change because it's not accelerating. So all the distributions of electric field will be same in each direction. But if if it is accelerating, let's say with some acceleration a t, the velocity will be like this. Uh, okay, so if it is the case, then what we can say is that this this concept, this concept that the field line will be same will not be valid because now what you have is something different. So if it is moving in some acceleration in x direction, so what happens? You have the charge here, and okay, so the charge will move some distance. So here what happens? It will move to some distance. this distance t, it will from here, and now what will happen? The field lines, if you draw the field lines, it will be like this, this, and this, and this. So here you can see this was the initial position, this is the final position. Now, if you draw any bigger Gaussian surface, so what will happen? If you draw something like now, uh, due to the Gauss law, what will happen? So if we consider this as a center, so from here, due to this Gaussian surface, uh, okay, so if this was the initial center. So for this Gaussian surface, what will happen? So if the initially it was like this, okay, let me use some different color. So this center, this is the new center, this is the old center. If we use something like this, like this, right? It also goes like this. It also goes like this. It also goes like this. Like now, now what happens here at this boundary? So if you pay close attention here, so it is not like continuous anymore. So uh, means it is continuous, but like how it to sustain this continuous condition, what will happen? So it will twist something like this. So here you see, if you notice it, so it will twist itself. They are the same in this direction. So it's only, but it is twisting like this, right? So there is this component, and this one is also twisting this component. This one from here, and then from here it is going. So it is also like this. So it means like this electric field lines now have been twisted, and so they have been introduced with a new field lines. It was here like this, and this, like from here, then it like this, like this. So like this. So that means up now we have this perpendicular field components that are at every point. So, and that is perpendicular to what? R cap. R cap is what? This is radial outward direction. So the we need to know what is the E perpendicular. That is perpendicular to R cap. So for that, we can just do a simple calculation. So if your initial charge was here, travels the distance Vt, then what happens for any given thing, like so if it moves some distance, so in this way it will be the same, but in this direction there will be much change, right? So this was change, this change is there, so it makes angle theta. So you can just write it like this. It is like this. So from here, that spectra, this thing, this radiation will also move from CT. Okay, the distance this field line will travel will be CT. So vacuum it will travel with CT. So you will have this is the CT distance at angle theta, and that angle theta is here also. So now what happens? Okay, so the acceleration was c tau. Okay, so that acceleration was c. So the distance, distance that is traveled, h, is the radial component r, and this is the tangential component e. So now what had happened here? This et. So means there was this which vector was this one. This one is now which have this component now. So okay. So we want to know this thing. So how we can this angle is again theta. So this distance is CT, and from here we can say that uh, this if it is moving with let's say velocity vt, so this is the perpendicular. So that means this is the vt cos theta, sin theta, and extend it. So from this distance to so this we know that this is vt sin theta. Now that's enough. So what we can do, we can just make this analogy here that okay, so the distance that we traveled was this c into the tau. If the acceleration is uh, tau, right? The acceleration was v by tau. So the distance that it traveled with this for this electric field was this much, c to tau, and this distance is after time t, it's c into t plus tau. This is distance that is traveled in the t time. Okay, so this means that this is the distance before t. This is the c tau. So if this much, so what will happen if we make this analogy like this is the c tau and this is the sin theta. So uh, we know this, and here is the same thing. So and the angle is same. If you make a like parallelogram out of it, so if you have this ER and E perpendicular, and you have this, so same. So we can easily understand that the both triangles are same. This one theta, this theta, this, this, and this two. This, this. So from here, one can calculate like this E perpendicular E R, and just have t sine theta. Okay, and the ER is proportional to the theta. This with this, and this thing is so we can just calculate the that is Vt sine theta was theta r, and we know that ER will be nothing but the distance at which we are calculating it, the field and the charge. So ER is like if you have this charge, if this is the distance r. So okay, sorry, if this is a charge and some distance is r here, something like this. So you can just write it down. The electric field is by q over 4 pi epsilon naught r square from this Gauss law. Okay, so now what you can simplify it, because you know that c tau is c tau is r, sorry, ct is r, and y tau is acceleration. So you can write cy tau is acceleration into sine theta into a into sine theta into the q by epsilon naught, but c into c by t. So it's like c is equal to r by t. This t will come in this denominator and then become c. Write c square and r. So we find out that this electric field becomes E sine theta over c square 1 over 4 pi epsilon naught q by r time. So here you see that electric field magnitude is proportional to 1 over r, right? So you can see that it's not 1 over r square anymore. And we know that this electric field that is here is changing with the time. So R is equal to, let's say, at CT some value, you have this electric field components like that was like this, all the electric lines were this, but R is equal to CT, but after some time delta T, C T plus tau, this is the distance CT plus tau, tau is the, that the acceleration, this tau is here, tau is right, tau. So this is the time parameter. So we have if now at some time around delta t, what will happen? This will this will not, this thing just shifts. So this means that it will go here, here, all the vectors will be here and here. So if you see in this area, so this is the change del E over del T. It's not zero because it's not uniform now. So and in this area also, the del E over del T is not zero. So this del E over del T is not zero. That means that del cross B zero, it's not zero. Del E over del T. And that if this is the del cross B, you can just calculate B dot dl. So you can make this since this. So what I was saying that okay, let me turn on the fan also. So I was saying that if you have this surface, so what will happen? You can calculate the B dot dl here. So it will be like del cross B translated to B dot dl, and so this will be like a dot dA. So this is the curl and this is the area integral. So, sorry, this is the line integral. So it's some path that you have drawn, and this is the surface of that area. So what will happen? You do the calculation. So the B magnitude will just come out to be uh, E magnitude, and upon the velocity c. Okay, so this will have this relation, and from here we can just write b perpendicular is equal to over c was c square here into 1 over 4 pi epsilon naught q over r, but divided by 1 by c. So this is the relation. Now so now if we think about this Poynting vector that the question was there, so E times B, so the magnitude of this Poynting vector, how it does, it depends on R, will be because you can see this magnetic field is also proportional to 1 by R, so we can just write it down, and then electric field is also proportional to 1 by R, so we can also write that down. So 1 by R multiplied, it's the proportionality is R square. So the Poynting vector is dependent on R by 1 over R square relationship. Now uh, let's go to our the slide. This question number 5. So where it was asked like if point charge is accelerating with A is equal to B by tau, then what will be the perpendicular component of the electric field? So it will be Bt sine theta cos this from here cos this was the similar the this was the Bt. So it traveled this distance c tau, the Bt sine theta. It was this Er, and this was the E perpendicular. So you just taken the ratio of this one. From here on that this distance like this. So it's Bt sine theta. That's okay. Over c tau into q over 4 pi epsilon naught r square. So We can see the electric field depends like, sorry, it's not R square. Okay, if we are doing this in this way, so it's R square now. But always you can just remove this, like you can divide this T in the down. It is it will be like V sine theta. C tau, tau is here. Q over 4 pi ln naught R by T to R. This R by T is nothing but the V this C is equal to R by T. Right. Yeah. Tau C square ln naught R. Again, you can go one step further. This P by tau is acceleration. Just write it. Sin theta over C square over 4 pi epsilon naught. Just A sin theta over C square over 4 R B, and then again you have the magnetic B. So B can be written as B was E mod of E over C C cube. So option A is correct here in this case. Now the next question is the amplitude of magnetic field component is. Okay, so what I was sharing is this, that so the question is now, the sixth question is the amplitude of the magnetic field component is. So we have just calculated it, like if you just calculate the integral around along that uh, Gaussian surface, so what you will have is this uh, that this B perpendicular have this relation A vector per C. So the time dependence comes in this electric field, and the okay, so you do this V dot dl equal to, because you can always write del cross B equal to mu 0 ln 0 E over del T. What you can do, right, ln 0 del E over dot dA, and now area integral, area, yeah, you can just change it to the surface integral B dot dl, and sorry, this line integral area integral mu 0 epsilon 0 del E over del T dot dA, and then from here you can just uh, for any arbitrary area, what will happen? This is nothing but 1 over mu 0 epsilon 0 is nothing but watch, you have C is equal to under root mu 0 epsilon 0, right? So this is 1 over C square, the B dot dA. So B particular, so that is perpendicular to the, propagation direction, and if you are field is like this, so if you're taking this integral, so this distance that is being traveled in this and in this way, so that is going to add up, right? and this is like this, and this is like this. So if it is okay, so what you can see, like if this is moving in this direction, electric field in this direction, so E cross B should be the direction. E is this, E is this, B is this, R R direction. So if you make like this, so you can see the area is in this direction, E direction. This and this are anti-parallel, so they will cancel out. And this one and this one. So we like squeeze delta. So we will have this B dot dl this way. It is like this, and this is this, and close integral is there. So we can say it will be like B into this dl equal to the area. Area is this is dx dy dx dy is dy dx e vector in z direction, so that comes out naturally. And have del E over del T. Del E over del T is nothing but that it's constant because this time will go away. So if you calculate the so E was okay. So let me share my screen again. Yes. So okay. Sorry guys, this there is this internet problem. So we know that the electric field is like this. Electric field was earlier that we have calculated was this. So from here we calculated that time. So this was the copy it. So if we del E over del T, we do this. So we can write sine theta over C tau Q over 4 pi epsilon naught 1 over R square. Okay. So from here, if you just put it here, so it will be like mu 0 epsilon 0 will be 1 over C square V by C sine theta over tau Q over 4 pi epsilon naught 1 over R square into the distance. This is the distance R. Sorry, so this distance dx is R here. So we have this dr into dy. So you just integrate it out. So okay, this. When you do this, so you can using this. What we can do, we can calculate the magnetic field. Magnetic field was B perpendicular is equal to E perpendicular over C. And from here, we can have okay. So first we calculate that paste this was this. We calculated the del E or del T. We like B sine theta, theta Q over 4 epsilon naught 1 over R square. Now, okay, now this B dot dl was, so the dl that survived was dy. So it will be B sine theta, C tau, and 1 over C square due to mu 0 epsilon 0. Okay, this one, and the del E or del T we have calculated. So we have B dot dl and then B dot dA. So we can just write dot dA will be df dr dy. We can just integrate from 0 to r and 1 over r square, and this one from 0 to y. So it will be like this one. So this B perpendicular will be 1 over C square B sine theta C tau 1 over R, and you can take the mod value here, and the dy will cancel out this one. So the B perpendicular will have it 1 over C uh, 1 over C cube. Okay, this H. and some proportionality constant that I haven't taken account, but you can see that the formula is very similar because this was the E field. So the E field. So just we can compare. So this CQ, this 1 over 4 by epsilon naught. Sorry, this one over R, and then E over tau and sine theta over C, and I think I made a mistake. So this Q over 4 by epsilon naught is here. So Q over 4 by epsilon naught should be there. So you can see here, this is nothing but the acceleration. This is the by C sine theta 1 over R and Q over epsilon. So if you just calculate it, so this will be like B perpendicular to A 1 over CQ A sine theta. This is the A. Sorry, this is the C square. This is C included here. Q over 4 pi epsilon naught 1 over R. Okay. So if we write it explicitly like this, so you can just compare that. This is nothing but the E field, C field. This is how you can just see the relation. And then the next thing is calculate. Uh, Next thing is to so we can also see that other options are not correct. Next question is, if the electric field component due to radiation is given like this, calculate the amplitude of Poynting vector. So we know that this amplitude is given by E perpendicular is equal to Q A sine theta over 4 pi epsilon naught R. Okay, so what you have, this is the electric field, so you can calculate the magnetic field. Magnetic field will be Q A sine theta 4 pi epsilon naught R into 1 by C, because B perpendicular was E perpendicular by C mod of this. So mod of S will be mod of E cross B, and we know that E and P are perpendicular, so sine theta will be 1. So there is no sine theta, just mod of this. So Q A sine theta over 4 by epsilon naught R into 1 by C, uh, Q A sine theta over 4 by epsilon naught R. Then this mod S is here, then mod S will be Q square A square sine square theta over 16 pi square epsilon naught square R square 1 over C. And from here you can just see the dependence Q square A square sine theta sine square theta over 16 pi square epsilon naught R square. This is the amplitude of S, and here from here you can clearly see that S is proportional to 1 over R square. Again, the last question that we have seen. And then we have calculated the Poynting vector. Now the next question is, power emitted from a point charge Q is proportional to Q square, does not depend on Q, depends on Q, depends on 1 by Q. So we can see that this S, whatever this is this power per unit time. right? So this means this pointing vector is tells us like how much power is being transmitted, being uh, it's flowing in the system per unit time. So we can see that it's proportional to the Q square. So SH what? SH SH the dimension uh, sorry, if you this is per unit area here. So this is the power. Sorry, power is energy per unit area per unit time. So this is the power. So power is given by this, and so from here we can see that the S H Q square A square sine square theta over 16 pi square epsilon naught r square. So from here we will have S that will depend on the 1 over r square, S that will depend on q square, S that will depend on the acceleration square. So all these things. Okay. So from here we can see that this S is dependent on the q square. And then again, for a point charge, if the simple harmonic motion is being performed, which of the following are true? So first we have to identify that xt is the position which is a sine omega t. So what you have to do? You have to actually calculate the acceleration. So acceleration will be like time derivative will give us the velocity. Dx over dt will be a sine of omega. That will be like cos omega t into omega. And this is the velocity. So this is the velocity vt. Now for the acceleration at, we have to calculate the dvt over dt, and that will be like a minus of sine omega t to omega square, right? So our acceleration is not dependent on minus a sine omega t omega square. Now what you can do, you can put it back in this equation here. So this is the acceleration, right? So you will see that dependence will be like q square. A square is here, a sine omega t omega square omega whole square and sine square theta 16 pi square and r square ln naught square r square, right? Ln naught square. Now what you can see that this st power per unit area per unit time is proportional to the k square a square sine square omega t omega power 4 sine square theta over 16 pi square square r square. So here we can easily see. Uh, sorry. So from here, okay, let me go back to this. So we first we have done, we have calculated the extra velocity, velocity. Then we have calculated the acceleration. So here is the acceleration. Then we put all this into the formula of this pointing vector. And then we have calculated the power. Sorry. So from here, we have q square, a square, sine square omega t, omega power 4, sine square theta, over 16 of pi square epsilon naught square, r square. Now what we can see, so we can see S is proportional to the q square, that already we know. S is proportional to the amplitude square of the acceleration that we know. But you can notice that it's proportional to the omega of 4 for this small acceleration that is being done with the like simple harmonic motion that is being done with the frequency omega. So the whatever the charge particle is that is going up and down in the omega with omega frequency, and that's why this power is not dependent on the omega of 4. The next question is the next question is charges. So charges this a charge is Q1 that has some charge. So okay, so Q1 has some 1 coulomb of charge, and 1 coulomb is equal to 1.6 into 10 to the power minus 19 C. And then there is this alpha particle. Alpha particle has 2 coulomb of charge because it's hydrogen helium nucleus and 2 electrons are removed, so plus 2 charge. So it has Q1 has this much charge, Q alpha particle has this much charge, coulomb. So this much. Now, what the question that we are being asked is how many both are accelerating at 10 meter per second square. Means the acceleration is same for both. Means the age 10 meter per second square for both the particle. Now, what we have to do, we have to find out how many more, times more power does that particle radiate compared to the proton. So we have just seen that S is proportional to the a square, q square from here. So we can see it does not depend on the mass. So it depending on the charge. Q is the charge. So for let's say for this Q1 it's 1 coulomb, and for alpha particle it's 2 coulomb. So we can clearly see that S that will be radiated will be like 1 coulomb. All the constants that are there, they will be there. Some constant A into the 1 coulomb square. So where the age a square sine square theta over 16 pi square epsilon naught square r square, and a is same for 10 meter per second for both. So we will be like bothering about this. So S will be a into 1 coulomb square, and that's a, but SQ1, but SQ2, S alpha, SQ1, this, but S alpha is what? S alpha is uh, charge square. So A into 2C square, and that's 4A. So this is like this. So S alpha is this. So the power of alpha and the power of Q1 has 4A over A, around 4 to 1 ratio. So alpha particle will lose more power than the charged particle Q1. And then the next question is, according to the classical electromagnetic theory, an accelerating charged particle emits radiation in form of, let me say it here. So, According to the classical electromagnetic theory, an accelerating charged particle emits radiation in form of electromagnetic waves. The energy of an accelerating electron should therefore. So we have seen that in previous question here that the alpha particle is radiating some energy, and also the charged particle is also radiating some energy. But since the energy is conserved, so whatever is being lost, uh, so the energy of that particle should decrease, right? So like if it is accelerating with some acceleration, it will lose its energy and its acceleration will decrease, and sometime it will stop. So that's why it is continuously decreasing, and it does not take a random value or anything because it's losing its energy in form of electromagnetic radiation. Okay, does anybody have any doubts in this or anyone? If not, then I would like to acknowledge Professor Manoj Kumar Hargul from IIT Kanpur, NPTEL team, PMRF team, and Department of Physics, IIT Kanpur for giving me such an opportunity. And uh, I will upload this video on YouTube and share this PPT with you, so where you can watch this later on. And all these PPTs and YouTube links for previous sessions are available on the log sheet that has been shared with you. So you can watch it there. Uh, okay. So we will meet next week at the same time from 5 to 7 p.m.